In this video, we're going to talk about power distribution, and we're going to specifically talk about both single-phase and three-phase power, and we're going to talk about how it relates to your air conditioning systems. So we have a few terms we need to discuss first. Single-phase. It's an AC current with two current carrying legs, L1 and neutral, or L1 and L2. Three-phase. It's an AC circuit with three current carrying legs, all with electrical potential to ground, L1, L2, L3, and I'll explain more about that in a few minutes. Hot conductor is any current carrying conductor that would show a potential to ground. In other words, if you take 1 meter lead and put it on a conductor and 1 meter lead and put it on ground, you will have a potential. You'll show voltage. Ground conductor, it's a non-current carrying conductor connected to ground. Could be colored green or it could be bare copper. Neutral, it's a conductor connected to the center tap of a transformer and ground. It's never fused, it's not equal to ground. It's a current carrying leg when it's energized. Equipment ground, conductor to equipment case and then ground. That's a safety. Sine wave, it's a chart representation, and we're going to show you this in a few minutes, of alternating current. Alternation, 180 degrees of a sine wave. Cycle, 2 alternations or 360 degrees of a sine wave. Frequency, it's the number of complete cycles in 1 second. Hertz, it's a measurement of frequency. In the US, 60 hertz is the frequency of alternating current. So 60 times per minute, we do a cycle, or 60 times per second, we do a cycle of the alternating current sine wave. Phase, it's a number of currents operating at different time intervals in a circuit. Peak voltage, it's the voltage at 90 electrical degrees in the sine wave. Effective voltage, what your meter reads, which is about 0.707 times the peak voltage. So this is an alternating current sine wave, okay? At 90 degrees is my peak voltage. That's point B. 0 is point A. C is back through 0. D is my peak voltage again on the negative side. And then we're back to 0 for a 360 degree circle. That's one cycle. One alternation is between A and C, or C and A on the negative side. This happens 60 times per second in the US. This is a three-phase sine wave, okay? Again, we go through cycles. We still have the complete rotation, 360 degrees, but we do it at 3 different phases on 3 different conductors. You'll note if you look at any point in time, there's no more than 1 phase at the 0 point. Okay, and that's something very important to remember as we talk about three-phase power. No more than 1 phase is showing 0 voltage at any point in time. So let's talk about single phase versus three phase. Single phase, again, has 2 current carrying conductors. 120 volts between L1 and neutral, or even L2 and neutral. 208, 230 volts between L1 and L2. It can be obtained from three phase. Single-phase motors require a starting device to protect the start winding. Okay, so in single-phase motors, you're going to have a capacitor most often, and you're going to have, if it's a capacitor start induction run, you're going to have some sort of start component to take the start capacitor out of the circuit. Three-phase has 3 conductors, 4 with neutral. Okay, three-phase is used on commercial and industrial application. Three-phase motors do not require any starting components. When you come across a three-phase motor, you're going to find a heavier motor. You're going to find 3 run windings, okay? They will all ohm out almost identically. Three-phase does not require start components. Three-phase motors are versatile. Single-phase power can be obtained from a three-phase supply. In other words, you can have both. And in a lot of package air conditioning systems, you will see both types of motors being used. If it's a three-phase system, the compressor may be a three-phase motor, but your outdoor fans or indoor blower motor might just be a single-phase fan. And again, single phase. You have one sine wave. Okay, we capture the north, we capture the south, and we capture the neutral. Or we capture L1, neutral, L2. Neutral is the center point. Three-phase power. We actually capture L1, L2, and L3, and sometimes they'll capture the neutral wire as well, not always. So how does power get distributed? From a power plant, the power enters a substation and is stepped up. Okay, what that means, we might take the 10,000 volts coming out of the power station and we'll step that up to 20 or 25,000 volts, sometimes higher. From the substation, it's sent across lines cross country. A secondary substation steps the voltage up or down based on the application. Okay, so we have our power generating plant, might come out of the plant at 13,800 volts, then it could be stepped up to 500,000 volts for high voltage transmission, and then it eventually will come down to step down substations along the way that will step it down to 13,800 volts for transmission along the roads, and then it will step it down at the pole or at the house even further to the 208, 480, or whatever we need in the homes. 120, 240. Okay. Now, once it gets into the house, okay, we've come now on the street. We have a transformer on the street. Okay, we have a neutral that's actually tied to ground. Okay, we have our line, which is going to be the highest wire on a pole. Then you come into your transformer. What we get out of that transformer is we take an L2, we take an L1, and we center tap it, and that's our neutral and ground. And again, notice it's all tied into a true ground, which is grounded outside your home or building. When we go across L1 and L2, we get 240 volts. Now we come through the power meter, okay, we come into the building, and we have a breaker panel. We have a main breaker usually, and we have a breaker panel. That breaker panel has two bars on it, okay, and that's L1 and L2. In the center, we normally have, or off to the side, we normally have a neutral bar, and we also have a ground bar you'll see in most panels now. They're actually tied together to a ground. So between L1 and L and neutral, you get 120. Between L2 and neutral, you get 120. The double pole breakers, which captures both L1 and L2, you will get 240. So the voltage enters the building consisting of a cable, a weatherhead, a conduit, a meter box, a panel box, and up to this point it's off limits to an HVAC tech. An HVAC tech in most states may not do anything inside the breaker panel or anything up to the point where the disconnect is near the equipment. So the panel box consists of fuses or breakers. It has a main disconnect and an individual circuit breaker. The main breaker has the rating for each line. Okay, so again, we have our branch breakers. Branch loads may not exceed the rating of each branch circuit. Everything is wired in parallel. Each branch load may not exceed the main breaker. Neutral comes from the center tap of the transformer, and ground is connected to the grounding rod, not to a water pipe. Branch wire color codes are normally very easy. Black is hot, white is neutral, red, could be hot L2, blue could be hot L3, and green or bare wires are ground. So understanding how power gets to the equipment and how power is broken down into the power panel and to get to your equipment itself is important so that you can understand the L1, the L2, the neutral, and how everything plays together. Some equipment, if you don't have a good neutral, it's not going to work.